Hello students. In last lecture, we have studied Gauss law and we have calculated the intensity of electric field due to a point charge with help of Gauss law. In this video, we will calculate the intensity of electric field due to a line charge with the help of Gauss law. The second application, intensity of electric field E due to a long line charge. Long, here this is infinite, you can say this is infinite line charge. Consider this is a infinite length wire having charge density, linear charge density lambda. This is linear charge density lambda is equal to Q over L. The amount of charge on per unit length is called lambda, linear charge density. Okay, we have to find intensity of electric field at this point due to this line charge with the help of Gauss theorem. Okay, this observation point is distance r from this line charge. Now, if we want to calculate the intensity of electric field due to a point charge, as you have seen in last lecture, then we have to consider a Gaussian surface. I have told you, if we have a point charge, then the shape of Gaussian surface for a point charge will be sphere. Just like this, the shape of Gaussian surface for this line charge will be cylindrical. Okay, then consider a cylinder of radius r and length L. Now we have to find intensity of electric field due to this line charge at this point. For this, we have assumed a Gaussian surface, cylindrical shape around the line charge. The radius of this cylinder is r and height of this cylinder is L. Now, before applying Gauss law, first we have to consider small area element on each surface. Okay, this closed surface is made up of three surfaces. Two are circular faces and one is one is curved surface. In Gauss theorem, we calculate the total flux passes through a closed surface. If we have a point charge, then the shape of Gaussian surface will be a sphere. Okay, a sphere is a single surface body. A sphere is a single surface body, but in this application, we have a line charge. To find the intensity of electric field due to this line charge at this point, we have to assume a symmetrical Gaussian surface which is cylindrical in shape. Consider this is a cylinder, this one. Then this cylinder is a closed surface which is made up of three surfaces. Two are circular faces and one is curved surface. Then in Gauss law, when we apply Gauss law, we have to find total flux passes through this closed surface. Or you can say, in applying Gauss law, we have to find total flux passes through all three surfaces. Okay? Then consider a small area element dA here, a small area element dA on this surface and dA on this surface. Okay, we have three surfaces in a cylinder. Two are circular and one is curved surface. The line charge is in this situation. Electric field at this point will be in outward direction as we know, the direction of electric field for a point charge will be outward, and here the electric field in this direction and same here in this direction. Okay, now we have to mention the direction of area vector. Then this small area element dA, then area vector will be like this in outward direction. We have a cylinder, and if we want to make area vector, consider this is a small area element, this one dA. Then the area vector for this surface will be perpendicular to this surface in outward direction. Okay, then dA is parallel to E in this surface. At this area vector perpendicular to this surface in outward direction, the area vector will be like this, and for this surface area vector this. Okay, then by Gauss theorem, by Gauss law, total flux passes through closed surface is equal to 1 over epsilon naught time of total charge. This is total charge or net charge, enclosed within closed surface. This term is total flux. Again, remember this. This is the net flux. This is the total flux passes through a closed surface. Then the total flux passes through this cylinder is the algebraic sum of flux passes through this curved surface E dot dA curved surface plus 2 times of flux passes through from circular face. Okay, is equal to value of charge lambda into L. This is a very important step. This term represents the total flux passes through any closed surface. In this problem, we have a cylinder which is made up of 3 surfaces. Then we have to calculate flux passes through each separate faces, which gives the total flux passes through this cylinder. Then this term, we can divide this term in 2 terms. Flux passes through curved surface and 2 times of flux passes through circular faces. Now, curved surface E dot d, as I told you, E dot dA is E dA cos theta, E dA cos theta, and for curved surface here theta is equal to 0 degree. This is cos 0 plus 2 times of E dot dA, E dA cos theta. Here for circular faces theta is 90 degree. Okay, remember this parameter theta, it is the angle between electric field and area vector. For circular faces, the angle between electric field and area vector is 90. Lambda L over epsilon naught. Then this term will be E dA cos 0 is equal to 1 plus 2 times cos 90 is equal to 0. Then this term will be vanished, is equal to lambda L over epsilon naught. Okay, got it? By applying Gauss law, this is total flux passes through the closed surface. We can divide this term into 2 terms. The total flux passes through the given cylinder will be equal to sum of flux passes through 1 curved surface and 2 circular faces. For curved surface, the angle between E and area vector is 0, and for circular faces, the angle between E and area vector is 90. So this term will be vanished. Now, E, we have to find E, integration of dA. This is summation of small area for curved surface. Then the curved surface for cylinder is 2 pi r. Okay, this is the formula for curved surface for cylinder is equal to lambda over epsilon naught. Then the formula is 2 pi epsilon naught lambda over, this is E is equal to 2 pi epsilon naught lambda over L into R. 1 over 2 pi epsilon naught, we can write this, this is lambda over epsilon naught, then cancel L from L, E is equal to 1 over 2 pi epsilon naught lambda over R. This is formula for intensity of electric field due to a long line charge. If you see, we have calculated intensity due to a point charge, which follows inverse square law. E inversely proportional to R square. This is for point charge. But in this formula, this is formula for intensity of electric field due to a long infinite line charge. This inversely proportional to R. Always remember this. This is a very important difference between intensity due to point charge and intensity due to a line charge. Their dependency of E with R. If you plot a graph for E and R, then graph will be like this. Now I am going to explain you intensity of electric field due to a spherical conducting shell with the help of Gauss theorem. This is third application. Intensity of electric field due to a charged conducting spherical shell. Here conducting means metallic. Consider, so in this lecture, in this video, we will find intensity of electric field due to a charged conducting or metallic spherical shell. This is third application. Consider we have a shell of radius r. This is center. It is a conducting shell. Let a charge plus q is given to this shell, which is uniformly distributed on the surface of spherical shell. This is charge plus q is given to this shell, which is uniformly distributed over the surface of metallic spherical shell. One thing you should remember, if we give some charge to a metallic conductor, it appears on the surface of metallic conductor. It does not reside inside the shell, inside the metallic conductor. Okay? If we give some charge to a metallic conductor, then it is uniformly distributed over the metallic conductor. Then in this situation, in this problem, we have given plus q charge to this spherical shell, which is uniformly distributed over this surface. Now, we have to find intensity of electric field due to this charged spherical shell at 3 points. 1 point we will take outside, 1 point we will take on the surface of a sphere, and the third point inside the sphere. Okay, then first we will take 1 point outside the sphere. So first case, when small r is greater than to capital R, it means observation point lies outside the spherical shell, outside point. We will use Gauss theorem. So first step. What was the first step to apply Gauss theorem? At first, we will draw a spherical surface. We will draw a closed Gaussian surface around charge configuration. As I told you, if we have a point charge, then the shape of Gaussian surface will be spherical. And if we have a line charge, then the shape of Gaussian surface or closed surface will be cylindrical. We are studying only symmetrical Gaussian surface. That's why it may be any shape or size, but in your syllabus, for a point charge, the shape of Gaussian surface will be spherical, and for a line charge, the shape of Gaussian surface will be cylindrical. Now, we have a spherical shell. So, always remember, a spherical shell, a charged sphere, can be treated as point charge. This is a very important part of electrostatic. If we have a spherical shell, if we have a spherical charge configuration, then we can consider it as a point charge. Reason I will explain you later. Okay. Now in this question, in this derivation, remember only charge sphere can be treated as point charge. The reason for this I will explain you later. So the Gaussian surface for this spherical surface will also be a sphere, a closed sphere. We will draw this Gaussian surface from dotted line. This is Gaussian surface. All distances should be measured from center of this sphere. Then the distance of observation point to the center of a spherical shell is small r. Then second step, we will consider a small area, draw direction of electric field at observation point, which will be in outward direction, and draw area vector, which is perpendicular to this small area element. Now from the Gauss theorem, E dot dA surface integration is equal to 1 over epsilon naught times of charge enclosed in Gaussian surface. Let's see, Gaussian surface is this, and inside this surface the total charge is only plus q. Then here put plus q, E dA cos theta. Theta is 0 degree. So cos theta, cos 0 value 1. Integration is equal to q over epsilon naught. Now E surface integration of dA q over epsilon naught. I have told you many times, the surface integration of this dA for a sphere will be 4 pi r square. 4 pi r square. Which r? We will take small r. dA is the small portion of Gaussian surface. Then while integrating dA, we will take total surface area of Gaussian surface. It means 4 pi small r square q over epsilon naught. E is equal to 1 over 4 pi epsilon naught q over r square. As you see, this expression is same as intensity of electric field due to a point charge. Now we can say, we can consider this spherical shell as a point charge, because for both the formula for E is same. So this is the intensity of electric field due to a spherical conducting shell at some outside point. Now second case, we will take second case. R equals to R on the surface. on the surface. Now observation point lies on the surface of this spherical shell. So again we have to draw a Gaussian surface which have same radius as of spherical shell. Now observation point here, this is R. In this situation R equals to capital R. Now same process, we can remove this Gaussian surface. Now consider a small area, draw the electric field. Electric field will be along this line in outward direction because we have positive charge, and draw area vector. Now again from Gauss theorem, E dot dA is equal to 1 over epsilon naught. The total charge inside this dotted Gaussian surface is Q. E dot dA, E dA cos theta, theta in this situation also 0. dA is equal to Q over epsilon naught E. Now dA, this is area of Gaussian surface, 4 pi small r square. In this situation, small r is equal to capital R. We can put here capital R. The surface area for spherical shell in Gaussian surface will same. E is equal to 1 over 4 pi epsilon naught Q over capital R square. This is the expression for electric field due to a spherical conducting shell on the surface of shell, which is same as previous case. It means electric intensity of electric field varies according to this relation on the surface and outside the surface. Now we will take third case. Let R is less than capital R. Now the location of point, observation point inside the sphere. I will again draw this figure. This is a spherical shell having plus Q charge uniformly distributed over the surface. This is center and this is radius of this shell. Now the observation point at which we have to find intensity of electric field lies inside the sphere. Consider the observation point is X. Join the observation point in the center of shell. This is radius R. Same process. Draw a Gaussian surface passing through this point, spherical Gaussian surface. Now, from the Gauss law, E dot dA is equal to 1 over epsilon naught times of net charge inside the Gaussian surface. I have told you, if we give some charge to a metallic conductor, it will appear on the surface of conductor. No charge will reside inside the metallic conductor. Always remember, if we give some charge to a metallic conductor, then it will appear on the surface of metallic conductor. Okay? In this situation, we have a metallic spherical shell. If we have given some charge plus Q to this shell, then total charge will appear on the surface of metallic conductor. No charge will reside inside the metallic conductor. Okay, then here don't need to draw dA and E because this is the Gaussian surface and the total charge inside this surface will be 0 because this is a metallic sphere. If we have given some charge to this sphere, all the charge will appear on the surface of sphere. No charge will reside inside the metallic conductor. So in this case, in third case, the total charge inside the Gaussian surface will be 0. So intensity of electric field will also be 0 inside a spherical conducting shell. This is a very important statement. Now you can say the electric field inside a metallic conductor is 0. Now if we plot a graph E versus R graph for a spherical shell, consider here R is equal to R, it means this point lie on the surface, and beyond this R is greater than R, it means outside the surface, and here R is less than capital R, it means inside the surface. On the surface, dependency is this. On the surface, the electric field will be maximum. This one. On the surface, the electric field will maximum. And outside the surface, the value of R increases, so E decreases according to this dependence. And inside the surface, no electric field is there. This is the intensity of electric field due to a spherical shell. In next lecture, we will do some numerical. Read it carefully, and if you have any doubt, ask me. Okay, you can comment.